Hello, this is Professor Deborah Chung. I'm going to talk about carbon materials, which is a topic of my research for about 45 years. And greetings from University at Buffalo, the State University of New York, where I work. I was born and raised in Hong Kong, and this is my family. I'm the little one here. My mother, Rebecca, joined the Flying Tigers in China as a nurse during World War II, and this is the headquarters of the Flying Tigers in Kunming, China. And this is the clinic where she worked. Very simple clinic with 4 nurses. And this is the outside of the clinic, the hospital actually. Very simple 1-floor structure. And during that war, China's eastern seaboard was closed off by Japan. So China's only way of communicating with the outside world is through the back door, which is the Burma Road, which links China across the Himalayas to Burma. Okay? And this road is very dangerous. However, Japan cut off the Burma Road after some time. And so even this backdoor route is out of the question. So the only way around that is to fly over the Himalayas, what's called the hump route. Very, very dangerous because the propeller airplanes at that time just weren't equipped to fly such high mountains. And there's not much communication, right? No computer at that time, so one wouldn't know what's the weather up there. So a lot of crashes of aircraft during that dangerous journey. And this is the propeller plane. You see just a simple ladder allowing the people to go up and down. And the pilot here and several mechanics, these are all from the United States. And this is my mother on her hump route. Okay, and you can see the passengers deplaning. And inside the aircraft, there are no windows. And my mother received some U.S. World War II medals for her work. And she wrote her autobiography, and there is an English version to that as well. But the Chinese version is available at this website free of charge, and you might copy that down, cnac.org/RebeccaChan01. Okay. In 1969, the first man landed on the moon. I was so excited. I was in Hong Kong as a high school student. I was so excited that I decided to leave Hong Kong for the U.S. For my university education. And so at age 18, I went all by myself to the United States. I studied at California Institute of Technology, a very good school, and this is how I looked like at that time. 76 Nobel laureates so far have been connected with Caltech. And in 1973, I graduated, and it turned out that I was one of the 4 first woman graduates of that university. I'm the right one, and here I'm the middle one. There, I studied electrical engineering, and I was particularly interested in integrated circuits. And I studied under Professor Carver Mead, the father of integrated circuits, 1972, very early for the teaching of integrated circuits anywhere in the world. However, somehow I got into research under Professor Paul Douay, the father of amorphous metals. And through him, I tasted research, which is the pushing of the frontier of knowledge. And that is super exciting to me. Now, nobody else knows that in the world. You are going to figure that out. And in particular, I learned about materials. Materials constitute the foundation of any technology, whether it's electronics, aerospace, automobile, construction, and so on. Okay? And also, if you look at the history of human civilization, every age, whether Stone Age, Bronze Age, or Iron Age, came by because of a certain material. So it's nice to be on the driver's seat of human civilization. After graduation from Caltech, I moved on to MIT, Massachusetts Institute of Technology, looking like this now. And there I pursued my PhD education in material science. And I was intrigued by the beauty of materials, particularly that of graphite. Shown here are the carbon atoms. So beautiful. And I chose to study under Professor Mildred S. Dresselhaus of MIT, a distinguished carbon scientist. Now, graphite has a layered crystal structure, with each layer looking like a honeycomb. Okay? And one can put certain foreign atoms or molecules in between those layers, forming a sandwich compound called an intercalation compound. And it turns out that the sandwiching involves some electron transfer between the host, which is the carbon, and the intercalate, which is the foreign species. As a result, the electrical conductivity of the graphite shoots up by orders of magnitude, so much that the graphite actually becomes a metal. It was very intriguing, not only to me and my professor, but to many people, other people in the world. And after graduation from MIT with my PhD degree, I continued in this field of research. So totally about 15 years of research on this particular field. However, I gradually saw the decline of my field of expertise. And a field of research can decline if the applications don't quite work out. Okay? And that was what's happening. And so I made a very difficult decision, which is to leave my field of expertise. Leaving is a difficult choice because I was already established in the field. People knew me and I knew them, and also, that was my only field of expertise. If I leave that, what am I going to do? It was like a blank piece of paper. And so that forced me to think out of the box. And thinking out of the box means the willingness to leave one's comfort zone. Okay? And that requires broad education because you need to know not just your little piece, but have background information outside. So having broad education would help a lot in jumping out of one's comfort zone. And also the willingness to cross disciplinary boundary. And so I was forced to jump out. And thus I pioneered a few research topics. Structural self-sensing, vibration damping through interface-derived viscoelasticity, electromagnetic interference or EMI shielding materials, and thermal interface materials. And I'm going to very briefly go through them. Now, the structural self-sensing materials pertain to cement as well as carbon fiber composites. Cement or concrete, that's really new for me. Never learned anything about that, never mixed cement in my life. But somehow I got interested in that, and with my electronic kind of background, I started to study cement as if it's an electronic material. A very crazy line of thinking, but it's through that crazy line of research that I invented smart concrete, which is concrete that contains a little bit of short carbon fiber, which alters the electrical behavior of that material in a way that the material's electrical resistivity changes in accordance with the deformation that the material experiences. Okay? Now, it's not just a matter of throwing in some short carbon fiber into the cement mix. One has to disperse the fibers very well. Okay? And these fibers are microfibers, a diameter of the order of 10 microns. Okay? And they tend to clump together like bunches. Okay? And to disperse the carbon fiber, it's very helpful to throw into the cement mix silica fume, which are submicron particles mostly. And because of these very tiny particles, their presence in the mix during the mixing, the whirling around of the mix, just mechanical action, it loosens up the fiber bundles. Okay. Concerning making a structural material be able to sense, the traditional way is to incorporate certain device, whatever sensor, into the concrete, say. Okay, just bury that inside. Okay, that is the route that everybody had been taking. However, my route is very different. I make the concrete itself a sensor so that there's no device incorporation at all. The advantages of having no device incorporation include low cost, high durability, large sensing volume, and the mechanical performance not compromised. There are numerous applications of the smart concrete that I invented, weighing trucks as they move because of the smart concrete pavement, also traffic monitoring enabled by that pavement, also the weighing of each room of a building to control the heating, cooling, ventilation, and lighting for saving energy. Yet another application is the sensing of vibration. Okay. And there are oil and gas wells as well as geothermal wells and carbon sequestration wells. And all these wells require the sealing of the well, and cement is used for the sealing. In this drawing, it seals the interface between the steel tubing called the casing and the rock. Okay? And the cement sees a lot of pressure there, and it's important to sense that pressure. You know, stress and strain are just two sides of the same coin, and so one can use the smart cement for the cement sealing here so that it becomes able to sense. Oil spill is a terrible thing that can happen if the sealing is not working. Now, having this carbon fiber cement is not enough. You have to be able to measure the electrical resistance change properly. Okay? And there are pitfalls of that electrical measurement. There are two methods of electrical resistance measurement. One involves 4 electrical contacts, the outer 2 for current, the inner 2 for voltage. And in so doing, your measured resistance does not include the contact resistance. Okay? Every contact has a contact resistance. You don't want to include that in your measured resistance because it's the specimen resistance that is what you're after. Okay? Now, if you instead use only 2 electrical contacts, then the measured resistance would include the contact resistance along with the specimen resistance, and that can be very wrong. Okay? So the advantages of 4-probe method over 2-probe method, the main advantage is that the contact resistance is not included in the measured resistance in the 4-probe method. Now, in the case that one is measuring the resistance while the stress or strain is changing, then there's a further problem, because as the material experiences the stress or strain, the quality of the electrical contact might change. Okay? And so the contact resistance might change as you impose the stress or strain. Okay? And that effect can even dominate, possibly even dominate the change of the specimen resistance with the stress or strain. So it's very important to take away the contact resistance from the measured resistance. A lot of papers have been published using the 2-probe method, and unfortunately, most of them have incorrect results. Now, if one measures the resistance along a direction that is very short, like a slab, and you want to measure the resistance along the through thickness direction, which happens to be very short, okay? and so short that it would be difficult to put 4 contacts, along in 4 horizontal planes. Okay, so when that is the case, then it's possible to use this non-ideal geometry of the 4-probe method. Namely, you have 4 contacts, 2 on each of the 2 opposite faces. The outer one is for imposing the current, and the middle one, smaller one, is for measuring the voltage. So it can be done, even if the material has a short dimension. And a lot of these techniques of electrical measurement are described in my book called Functional Materials. So the effect of stress or strain on the electrical resistivity of a material is known as piezoresistivity. Now, this has nothing to do with piezoelectricity. And the severity of the piezoresistivity is described by the gauge factor, which is defined as the fractional change in resistance per unit strain. For the case if the resistivity doesn't change with the stress or strain, but just the dimensions changing, then the gauge factor is typically 2 or less than 2, depending on the Poisson's ratio. But if it's the resistivity changing on top of the dimensions changing as you apply the stress or strain, then the gauge factor can exceed 2 greatly, even a few hundreds. Okay? And so the sensing becomes much more sensitive if you have the resistivity changing. That is piezoresistivity. This is an example of the resistance change in the case of carbon fiber cement under repeated compression. The thin curve is the strain along the direction of compression, and the thick curve is the fractional change in resistance in the same direction. And note that I have arbitrarily having a progression of strain amplitudes, a little bigger, and so on, and I follow that in terms of the resistance. And you can see the resistance increases. I'm sorry, the resistance decreases. The resistance decreases whenever one compresses. Okay. Now, one can take the resistivity at the peak strain of each cycle and plot that versus the strain, okay? And connecting the points chronologically, and one can see that there's not too much hysteresis. It's more or less linear, and that shows that it really works. The resistivity is responsive to the strain, okay? And this is the result using the 4-probe method. However, if one uses the 2-probe method instead, this is how the data looks like. Okay, it's terrible. Just doesn't work. Okay. Now, very often for structures, we deal with bending, beams under flexure. Okay. Under that mode of loading, flexure, then the upper surface and the lower surface experience different kinds of loading. Okay? One surface is feeling horizontal tension, the other surface is feeling horizontal compression as you bend this beam. Okay? And so under this situation, the way to do it is to measure not the volume resistance, but the surface resistance by using surface electrical contacts. I have 4 on each of the 2 surfaces. And in so doing, one can monitor each of the 2 surfaces in real time during the bending. Now, some people use this geometry for the electrical contacts under bending. They just wrap the electrical contact all the way around the beam. Okay? Again, 4 contacts, it's 4-probe method, but each contact is wrapped all the way around. Okay? Now this electrode geometry would not be suitable under flexure because you are just kind of averaging out the effects of the two opposite surfaces which behave differently. And you're just averaging out the two oppositely behaving surfaces. And so one would get very little effect. The sensitivity would be very small. And some papers have been published using this method. So it's very important to use the right electrical method. And using this method, I looked at carbon fiber cement again, but under flexure. And this is the surface resistance on the compression side. And the thin line is the mid-span deflection. It's a gradually increasing degree of bending. And the thick curve is the fractional change in the surface resistance on the compression side. And it decreases every time you flex it. Okay? And that agrees with what we observe under uniaxial compression, which again involves the resistance decreasing as you uniaxially compress. And here in the compression side, again, it decreases. On the tension side, it just does the opposite. The resistance increases. Okay? And on the tension side, it's particularly prone to damage. Cement is a brittle material. The brittle materials in general are very prone to damage under tension. And you can see that this damage gives rise to an irreversible increase in the resistance on the tension side. And obviously, when it breaks, the resistance shoots up. Now, the cement resistance also reflects the temperature, in addition to the damage inflicted by what's called freeze-thaw cycling. Now, cement gets damaged because of cycling between freezing and thawing temperatures. Okay? So here is the fractional change in resistivity. It's uniaxial compression, and it's versus time, but the temperature is cycled, as shown by the thin line, okay, cycled between freezing temperature below 0 and thawing temperature above 0. Okay? And every time the temperature increases, the resistivity goes down. Okay? And that is because there is some activation energy involved, some energy barrier involved in the electron jumping across certain interface in the material. And so the higher temperature, the easier is the jumping, and so the lower is the resistivity. So actually, the cement is a thermistor. A thermistor is a temperature measurement device that functions by the resistivity changing with temperature. So the cement is a thermistor. Okay? And note that as one cycles the temperature, both the upper envelope and the lower envelope goes up. Every cycle it creeps up a little bit. Okay? And that is due to damage. Okay? And this means that damage is incrementally inflicted on the cement in every cycle. Every cycle. It keeps having the damage inflicted until it dies, fractures, and it fractures at the coolest point of the last cycle. Okay? And it turns out that freeze-thaw durability is a big, big topic in the field of cement. Okay? And this is the first time anyone has been able to look in real time the process of the freeze-thaw cycling damage. Another area is vibration damping. Okay? That means, the amplitude of the vibration gradually goes down. That's what it means. Numerous applications, because essentially all structures doesn't like to be shaking around. So damping is needed for bridges, also for railroad, particularly high-speed rail. And it's important to reduce the vibration, but also to absorb the sound so that you reduce the sound. Okay? Now, the sound wave is a mechanical wave also. Okay? So the science is pretty similar between the reduction of the vibration and the reduction of sound. The vibration, the frequency is different, but the science is somewhat similar. In general, there are two types of structural vibration control, passive control and active control. Passive control means energy dissipation. Just naturally, the mechanical energy is dissipated or consumed. Okay? The active control means you use sensor and actuator in a synchronized fashion. Just like here, you have the primary disturbance, which is the disturbance, and then you have you sense that, and this output of the sensor tells the actuator to poke at this beam so that it gives a canceling signal, so that after the cancellation, what remains is very, very small signal, okay, like nothing. And this works very well. It's brute force, right? When it vibrates upward, you poke it downward. When it vibrates downward, you poke it upward. It's brute force, but it's very, very expensive. And so most attention, as far as I'm concerned, is on passive damping. Another manifestation of passive damping is that the material that has that capability has viscoelastic character, so that the stress and strain waves are a little out of phase. Okay? And because of that, when you have the stress-strain curve, upon loading and unloading, the loading and unloading curves do not exactly overlap. That means there is energy that's lost, right? Because the area under the curve is the mechanical energy per unit volume. And so the mechanical energy per unit volume input to the material during loading is greater than the mechanical energy per unit volume that's output during the unloading. So input and output are not equal, so you have some energy lost, and that is called the dissipated energy. They also call it storage energy. But anyway, that's the energy that's killed. Okay, but there's conservation of energy. You cannot just kill energy, right? It's just conversion of one form of energy to another, and mostly the mechanical energy is converted to thermal energy. Okay, and so this kind of hysteretic behavior is typical of viscoelastic behavior. So the bigger is this hysteresis loop, the better. Okay. In contrast, if you have a purely elastic material, the stress-strain curve would be simply a straight line, loading and unloading curves exactly overlapping, so there's no hysteresis, and so there's no capability of consuming the mechanical energy. Okay, so that's not what we want. We don't want purely elastic material. We want viscoelastic material. Okay, rubber is perhaps the most famous viscoelastic material. It has long bent molecules. As a result, the molecules can move, and the segments of the molecules can flap, and such motions can give rise to the dissipation of the mechanical energy. Okay? However, rubber is too soft. Okay? Energy is like force times distance, right? You have a lot of distance, but very little force. The energy is still very little. Okay? And that's what's happening to rubber. Because it's too soft, it's not able to kill much energy, in spite of the fact that it can deform a great deal. Okay, and we know how soft rubber is. Okay, and because it's so soft, the way people use the rubber or such polymers for vibration damping is typically to sandwich this green rubber between two stiff plates, say steel plates. Okay? So the steel plates constrain the green rubber, and it allows the overall system to be stiff enough while the rubber provides the mechanical energy dissipation. Okay? However, this method called constrained layer damping has a problem. Namely, this interlayer, this green thing, degrades the strength and modulus, right? Because it's soft. You're adding a soft thing into a stiff thing. So the more the soft thing you put in, the worse is the strength as well as the modulus of your structure. So it's not ideal. In general, using rubber or such polymers for damping has serious disadvantages. Low stiffness, that is very soft, low strength, as well as poor durability. A lot of plastics or polymers, including rubber, would degrade under the sun, right? We all know rubber bands, after a long time, they would not be effective rubber bands anymore. They just become brittle. However, my vision is to use structural materials for damping. That's actually a wild vision. Because structural materials have to be stiff, otherwise they would not be qualified to be structural materials. And to use structural materials for damping is just out of the mind of anybody. However, there are serious advantages of that. High durability, high stiffness, and large volume. The volume matters because this hysteresis area corresponds to the energy consumed per unit volume, So if you have a bigger volume, you would dissipate more energy. So having a big structure be contributing to the damping really pays off because it's so big. Okay? But if you just rely on the little piece of rubber, it's not such a big volume. Okay? However, one needs some new science to be able to get a stiff material, like a structural material, to be able to have viscoelastic character. And that is what I dreamed of and realized, and that's what I call interface-derived viscoelasticity. It involves a material that has a lot of interfaces in it. Okay? Upon vibration, there can be very, very slight slippage at the interface. And that very slight slippage causes the energy to be dissipated. Okay? So this is a different mechanism of energy dissipation, different from the rubber case. Rubber doesn't rely on interfaces. It relies on the molecules flapping. Okay? This is just a different mechanism, different science altogether. But this mechanism requires plentiful interfaces. If you have very few interfaces, the effect would be too tiny to be meaningful. But nowadays we have nanotechnology. We can have a lot of interfaces in a nano-structured material. And so it's possible to have a lot of interfaces, and so that the interface-derived viscoelasticity becomes appreciable. So using the interfaces, I developed structural materials that are both stiff and able to dampen. An example, actually it's the first example that I provided to the world back in 1998, is adding silica fume to cement. Okay, silica fume is tiny particles, mostly submicron, and one can add that to the cement mix. Okay, and because it's tiny, the presence of the silica fume particles gives rise to a lot of interface. It's the interface between the cement matrix and the silica. Okay? And because of the plentifulness of this interface, between the silica and the cement, one has enough interface for the interface-derived viscoelasticity to be substantial. But at the same time, the silica fume acts as a reinforcement, making the cement stiffer. So one has a situation in which the addition of the silica fume in the cement makes the cement stiffer. In addition, it makes the cement more able to dissipate mechanical energy. And having both the stiffness and the mechanical dissipation ability both enhanced is something that the scientific community had a hard time accepting when I presented that in 1998. Because they are used to thinking in terms of rubber. You know, if you modify the rubber so that it becomes stiffer, then that rubber would have less ability to dissipate mechanical energy. You know, so you get one and lose the other. Okay, you cannot have both attributes being enhanced, and that's kind of against their thinking. But it's possible because I'm dealing with a different type of science, namely interface-derived viscoelasticity. Now I switch to another topic, which is about electromagnetic radiation, interfering electronics and needing shielding of the electronics. Okay? There are numerous types of electromagnetic radiation sources. You have microwave oven, you have mobile phones, you have TVs, you know, all these. The lamp, fluorescent lamp also. Lots and lots of devices in our daily life that emit electromagnetic radiation, particularly radiation in the radio wave regime, as well as microwave regime. And it turns out that the radiation in that regime can interfere with electronics because electrons are in the electronics. And the electrons feel the electric field and get interfered. Okay? And as a result, we need to protect electronics by using certain material so that it blocks the radiation from getting into the electronics. In addition, you need the shielding material to shield the radiation from coming out of the radiation source, such as your cell phone. You need to shield your cell phone so that the radiation doesn't get out of it. So one needs shielding materials. This is an example of a carbon fiber composite computer casing, okay? And carbon turns out to be a good shielding material. Okay? The factors that govern the shielding effectiveness, traditionally, it's the electrical conductivity. Okay? The higher conductivity, the better is the shielding. So that's been used for a long, long time as the specification for how good is the shielding material. However, what I realize is there's another important factor that people have overlooked, and that is the surface or interface area. Okay, surface of the material, how much surface area, or if you have like a composite, that you would have the interface between the different components of the composite. So whether surface or interface, that area or amount of area per unit volume, that needs to be high. The higher, the better. And that's the new criterion that I put forth. Why the surface area or interface area matters is because of the skin effect, which means that the electromagnetic radiation can penetrate the conductor to only a limited degree, so that the electric field decays exponentially as it goes into the material. Okay? And so if you have a composite with the matrix being like a polymer or cement, which is not very good in shielding, and you have some some fillers which are conductive, and these, you have interface between the filler and the matrix, okay? And the electric field goes into each piece of the filler, but it decays exponentially as it enters that piece of filler. And so if you have a big fat fiber, okay, the inside of it is really wasted because the electric field cannot get into it, okay? And so you're wasting the goodness of your filler, okay, just by using the surface part of it, and the interior part of it is wasted doing nothing, okay? So it would be much more effective if the filler is tiny, tiny, okay, comparable to, say, the skin, that so-called skin depth, how much the radiation can penetrate. And so tiny fillers, nano size, okay, would be very good, okay. And having a lot of such interface area per unit volume would maximize the extent of interaction between the radiation and this filler, and so making the overall composite better in terms of the shielding effectiveness. Okay. And as the age of nanotechnology matures, the feasibility of using nano fillers to enhance the shielding effectiveness becomes more and more realized. There is a form of graphite called exfoliated graphite, and it's puffed up, okay? And it's like having a cellular structure, a lot of pores inside. Because of that structure, it's got a lot of surface area per unit volume. And if you have a pile of such exfoliated graphite and compress that, you have mechanical interlocking among the different pieces of exfoliated graphite so that you get a sheet without the need for any binder. And this sheet is flexible. So it is called flexible graphite. Okay? It's simply compressed exfoliated graphite. And this material turns out to have very, very good shielding effectiveness. 130 dB. We reported that back in 1996, and it's still the record. Okay? In fact, this is the limit of feasible measurement. You can't measure it if it's beyond this. And the reason why it's so good is that not only is the graphite conductive, it has the flexible graphite, because of the fact that it comes from exfoliated graphite, has substantial surface area per unit volume. Okay. Now, another nice feature about the flexible graphite is that due to the compression, the compaction of the fluffy stuff, exfoliated graphite, in forming the flexible graphite, you have the orientation of the carbon layers in the plane of the sheet, giving rise to a resiliency, springiness in the direction perpendicular to the plane of the sheet. And this resiliency is needed for gaskets. Okay? And so this material is superb for EMI gasketing. Okay? EMI gasket means you have, say, a box, which is the EMI shield, but there are seams in the box, okay? And you need an EMI gasket to fill out the seams to make the overall box a better shield, okay? And to get both resiliency and high shielding effectiveness in the same material is not easy. But with flexible graphite, we have that combination very well. Yet another issue is overheating of microelectronics. This overheating limits the further miniaturization of electronics. It limits the power also limits the reliability. Is the number one headache in the electronic industry. One way to alleviate this problem is to improve the thermal contact between the heat source, which is, for instance, the microprocessor, and the heat sink. Okay? And in order to improve the thermal contact, one puts in a thermal interface material. Okay? And the thermal interface materials needs to be very conformable to the surface topography of the two mating surfaces. If the conformability of this thermal interface material is not so good, you would have some air pockets left behind at the interface. And air is a thermal insulator, and so that's bad. Okay? So you've got to have the thermal interface material be very, very conformable. Having this interface material be just thermally conductive is not good enough. One has to have high conformability. So these are the two factors that govern the effectiveness of a thermal interface material. One is the traditional factor, which everybody knows. That's the thermal conductivity. But a factor that people didn't realize until I put forth that concept back in around 2003 is the importance of conformability. Okay? And it turns out that carbon black is very, very conformable because it is in the form of aggregates of nanoparticles. And so you can compress it a little bit and it squishes down and becomes like this. Okay? So it conforms to the shape of whatever surface that you're pushing into it. And I call it squishability, which means compressibility, and that results in high conformability of the carbon black solid. There's no other form of carbon that has such squishability, like carbon nanotube would not be squishable like this. And because the carbon black, even the solid, is squishable, if one makes a paste out of carbon black, one gets a superb thermal paste, which excels due to its conformability. Okay, so now I'd like to give you some basic information about the variety of carbon materials. This is a book of mine on carbon materials. Carbon is just one element in the periodic table, but out of that one element, you have many, many fantastic materials. There are three allotropes of carbon: graphite, diamond, and fullerene. And I'm focusing on the graphite allotrope family. All these are members of the graphite family. Okay? And I'm going to go through these as time allows. Okay? Graphite, tribostratic carbon, carbon fibers, carbon nanofibers, carbon nanotube without the cap, intercalated graphite, exfoliated graphite, flexible graphite, graphene, activated carbon, which is porous carbon, and carbon black. Okay? Graphite has a layered structure. Okay? So in-plane bonding is covalent and metallic. Out-of-plane bonding is van der Waals. So graphite is very anisotropic. And you have in graphite AB, AB, the ABA, okay, stacking, edge view and top view. Okay? And now the electronic configuration of carbon is 1s2, 2s2, 2p2, like this for the ground state. And one can excite this 2s to the 2pz position, orbital, and you get 4 unpaired electrons. And you can mix the 2s and the 2px and 2py, what's called sp2 hybridization, and that gives you these in-plane covalent bonds. While the 2pz electron that's left behind from the hybridization would get smeared and give rise to in-plane metallic bonding. And that's why graphite has high thermal conductivity as well as high electrical conductivity in plane, but it's basically an insulator in the out-of-plane direction. Between the planes, it's just van der Waals bonding. Okay, so it's easy sliding between the layers, and that's why graphite is a lubricant, and that's why we can write with graphite pencils. And I already mentioned about the metallic bonding giving high in-plane thermal and electrical conductivity. And because of the metallic bonding, there are numerous electrical applications of graphite, including electrochemical electrodes, whether batteries, supercapacitors, and so on, heating elements, electrical contacts or electrodes, brushes, which are sliding electrical contacts, also electronic device components. Now, there are many types of graphite. Natural graphite you can mine from the ground. Okay? It's a mineral, and you can write it like pencil. You can also make synthetic graphite by taking some coke particles and some pitch as a binder, and mix the two together, put it into a die, which is a mold, compact that under high pressure, and then heat that to high temperatures, and it becomes a chunk, and that's synthetic graphite. Okay. And this chunk can be very big. This big size is actually a graphite electrode that's used for metal oxide reduction to make metal. It's a big industry requiring such big graphite electrodes. Okay. Turbostratic carbon, on the other hand, is not so ideal as graphite in terms of the structure. There is irregular stacking, that is not AB, but it's kind of no such registry between the layers. And that is in contrast to the ideal graphite case where there is regular stacking, that is the AB, that registry. In turbostratic carbon, there is no registry. In addition, in turbostratic carbon, you have the layers not very nice. Okay? They are a little crooked. They are not extending it, not very extensive, and the parallelism is also limited. Okay? But still, there are layers. Okay? And because of this situation, there's no three-dimensional unit cell. Right? It's just a little random in a way, but it's still layers. Okay? So this is amorphous carbon, but it's not amorphous in the sense that all the atoms are random relative to one another. Okay? It's just no long-range periodicity. There is still short-range order, no long-range order, and that's the definition of amorphous materials. So turbostratic carbon is a form of amorphous carbon. Now, there is a process called graphitization, which can convert turbostratic carbon to crystalline graphite, and that's simply heating to a high enough temperature so that the atoms have enough thermal energy to move without melting. Okay? And they would automatically move so as to become more crystalline, okay? Converting the turbostratic carbon to graphite. And this conversion occurs automatically upon heating to enough temperature because the ideal graphite is the thermodynamically stable state, whereas the thermostratic carbon is not thermodynamically stable. We say it's metastable. Okay? And so if you give it enough thermal energy, anything metastable would want to change to the thermodynamically stable counterpart. And that's what's happening in graphitization. It needs high temperatures like 2,000 to 3,000 C, and it needs an inert atmosphere. And upon such graphitization, the X-ray diffraction peak shows up. Before, it essentially doesn't show up. Okay. The properties of turbostratic carbon are quite different from that of ideal graphite. They are less conductive, lower in modulus, but high in strength. The high in strength is because the layers are not so flat, and so it's harder for the layers to slide with respect to one another. And the turbostratic carbon is lower in oxidation resistance than the graphite, but they can be activated to form activated carbon more easily. And the turbostratic carbon cannot be intercalated. Now we go to carbon fibers. Carbon fibers in continuous form is widely available now. It's got high strength, high modulus, and low density, so it's wonderful for lightweight structures such as aircraft. Okay. Now, carbon fibers have a microstructure that differs greatly from graphite. This is synthetic graphite. In synthetic graphite, you have these graphite crystallites kind of randomly oriented. But in the case of carbon fiber, you can see that the carbon layers preferentially are along the vertical direction, that is the fiber axis. However, the skin has the carbon layers more parallel to one another than in the inner part called the core. See, the carbon layers are more crooked, though still preferentially oriented vertically. So we call it a skin core heterogeneity. Okay. The making of carbon fiber involves typically a polymer fiber. The most common polymer fiber is PAN, polyacrylonitrile, and it's subjected to oxidation at a low temperature so that it wouldn't melt upon subsequent heating. And then it's subjected to carbonization so as to convert the polymer to carbon. But it's not graphite yet, not the ideal graphite yet. It's just carbon. And then if you want it to become graphite, then you have to follow that with a higher temperature heating, the graphitization process. Okay? If you do the graphitization process, you would end up with high modulus carbon fiber. But if you skip the graphitization process and stop at the end of the carbonization process, then you would end up with high strength carbon. Okay? So there are various grades of carbon fiber depending on the temperature that you use to fabricate the carbon fiber. We call that heat treatment temperature. That's the fabrication temperature. Okay? And the tensile strength drops if it becomes more and more graphitic. But the modulus keeps going up as it becomes more and more graphitic. So you would have high modulus fiber here, but low strength fiber, here. Oh, no, I'm saying here's low, let me say it. This is high modulus and low strength, right? High modulus and low strength if you have a high temperature heat treatment. But if you have a lower temperature kind of heat treatment, the modulus is low, the strength is so-so, but actually here you can have maximum strength. So here would be high strength, but low modulus. So anyway, you have a gradation of many grades of carbon fibers. And depending on the heat treatment temperature, you have the carbon layers looking different. Okay? The higher the temperature, the more extensive and the more parallel and more flat are the carbon layers. Okay? The carbon fibers that are commercially available are in the form of bundles called tows. Okay? Looking like this could be 12,000 fibers in a tow, for instance. And here, there's no twist in the tow. But it's possible for there to be twist in the tow. So when you purchase, you have to make sure you buy what you want. Another form is you have the carbon fibers lined up, and they form a sheet, okay? And they can use some sewing to make the fibers not spread out too much. Okay, the fibers are in this direction here. Okay, the sewing is in the perpendicular direction shown in yellow. So this unidirectional carbon fiber sheet is convenient for being stacked to make a laminate. Okay, and you can stack in different orientations for the fibers in the different layers. Okay, and we call this the fiber layup configuration. And so it's up to the engineer. I want it stronger this direction, stronger that direction. You have a choice. Okay. However, this layup situation has one problem, which is it's mechanically weak and low in thermal conductivity in the through thickness direction, in the through thickness perpendicular direction. No fibers in that direction. So it's mechanically bad, and the thermal conductivity is low. Now, the thermal conductivity turns out to be very important for aircraft, because the aircraft, as particularly the engine part of the aircraft, gets hot, and you need to get the heat out. One way to alleviate that problem is to do sewing again, stitching. Yeah, this yellow thread. Okay. In the fiber preform, before you put in the polymer matrix, so it's still easy to sew, then at that point you do the sewing. Okay. A simpler way is not to do the sewing, but do needling. You have needles, and you just poke the preform with needles so that you have some vertical fibers, okay, due to the needling. Okay. Now, within one lamina, you have typically dozens of fibers stacked up. Okay, this is one layer, one lamina. Okay, and between one lamina and another lamina, note that the fibers are differently oriented in the two laminae shown. Between the two laminae, you have an interlaminar interface, which is a polymer-rich region. Okay. And because the interlaminar interface is a polymer-rich region, one can put nano stuff in there. We call nanostructured interlaminar interface. The carbon fibers are in the micrometer scale. Okay, so you have micrometer fibers and you have nano fillers. So you have two different scales, and so they call it multi-scale composite, also known as hierarchical composite. Okay. Now, the reason why people like to have this hierarchical composite is twofold. One is to improve the through thickness thermal conductivity, because the polymer is a lousy thermal conductor. And because of that, the through thickness thermal conductivity is bad. But if you put in some nanofiller in the interface here, that's thermally conductive. It would help the thermal contact between these layers, thereby helping the thermal conductivity in the through thickness direction. Another reason is to improve the interface-derived viscoelasticity. That is, you have nanofiller, so you have interface between the units of the nanofiller and the matrix. And so you having plentiful interface there would allow the interface-derived viscoelasticity, thus improving the vibration damping ability of this composite. This is an ideal situation of interface-derived viscoelasticity, where you have the interface being aligned, vertically aligned, carbon nanotubes in red. Okay? So as this crack opens, these nanotubes would get pulled out of the sockets, pulled out, and so this pull out involves friction, and so it consumes mechanical energy. Okay, this is great because carbon nanotubes are so tiny, so you have lots of interface area. Okay, however, this is idealized because when you put nanotubes in between the layers, the nanotube would naturally lie down instead of standing up. Okay, but this concept is still very nice. Okay. Now, the stuff in between the carbon fiber laminae is called an interlayer. Okay, in gray here, an interlayer. The nanofiller is actually only one of the types of interlayer. Actually, the most common interlayer, one of the most common, is a polymer that is put in for enhancing the vibration damping. Okay, like rubber, the polymer akin to rubber, by being an interlayer, would make the overall composite be able to have more viscoelastic character. However, this improvement in the viscoelasticity is at the expense of the strength and modulus of the composite. Another type of interlayer is the honeycomb sheet. Okay, this is a very thick type of interlayer, and because there are lots of holes in the honeycomb, the presence of this honeycomb would greatly reduce the density of the composite. Okay. The carbon fiber is also available in the form of cloth or fabric. Okay. And now in the weaving, it involves the bending of the fibers. And this bending actually is not ideal because each fiber is very anisotropic. When you have it bent, you are presenting the not so good directions of the fiber to the direction that's being loaded. And so the performance becomes not so good, comparing the woven fiber case to the non-woven fiber case. However, the cloth is very convenient to be handled. You just throw them one on top of the other, stack them up. And so people use the cloth quite a lot. But for the very high performance composite, like for the aircraft, they would not use the cloth because they don't want the bending of the fibers. So weaving, there are big weaving machines. There's also braiding machine. Okay. And this is a braided carbon fiber tube, and one can infiltrate it with the resin and make a tubing out of it. One can even do three-dimensional weaving. And now the three-dimensional weaving, it would overcome this mechanical weakness and low thermal conductivity in the through thickness direction, that problem that I mentioned earlier, right? You have fibers, whatever material, vertically, okay? So that's really the ultimate way to alleviate this problem. However, the 3D weaving is kind of exotic, and it's not as conducive to fabricating composites, right? If you just stack up the layers, it's convenient to make a certain composite structure. But if you want three-dimensionally woven form of composite structure, you really need to tailor-make your composite structure. Another way to make the composite is by filament winding. You use the spread toe ribbon, and you wind it on a mandrel, winding it like this in various prescribed directions. It can be huge. Okay. Another form of carbon fiber is in the form of a mat, also called a veil, also called paper. It's made just like making paper, but it's using carbon fiber, not the cellulose fiber used for regular paper. Okay, but it's similar in that sense. It's made the paper making process, and you have fibers that are randomly oriented in plane. Yeah. And there are applications of that, particularly in electrochemical devices where you need gas to penetrate this conductive medium. Also, there are chopped carbon fibers and milled carbon fibers, which are even shorter than the chopped ones. Okay? And in general, one can use the continuous fibers or the short fibers as a reinforcement to make a structural composite. Okay? However, for the case of concrete, okay, using fibers in concrete, the short ones are much better off than the long ones because you cannot throw the long ones into the cement mix, right? You have to lay them down. You cannot throw them into the mix, okay? Not only that, these continuous fibers are in the form of tows or bundles. Okay? It could be 12,000 fibers in the tow. And the cement is not so fluid, okay? And it's hard for the cement paste to penetrate the space between the adjacent fibers in the tow, okay? So you would end up with a situation where there's a lot of porosity due to the emptiness between the fibers in the same tow, due to the fact that the cement paste cannot get in, okay? But if you have short fibers, that problem is much less, okay? The dispersion of the short fibers can be enhanced by the silica fume, as I mentioned before, okay? On the other hand, in general, continuous fibers are more effective for reinforcing than the short ones because of the fact that the interface is not perfect. And that is, the bonding at the interface is not perfect. Because of that, the long ones are actually more effective than the short ones. One can also coat the fibers with a metal such as copper or nickel, okay, by a process such as electroplating, and that would greatly enhance the conductivity of the fiber. Okay, the metals are a few orders of magnitude more conductive than the carbon or graphite. There are numerous advantages of carbon fibers: low density, high tensile modulus and strength, low thermal expansion coefficient, thermal stability in the absence of oxygen to over 3000 C, excellent creep resistance, chemical stability, particularly in strong acids, biocompatibility, high thermal conductivity, low electrical resistivity, availability in a continuous form, and decreasing cost over time. But there are still some disadvantages. The anisotropy, the axial direction versus the transverse directions being different in property. Low strain to failure, and it's still a kind of brittle. Compressive strength is low compared to the tensile strength. And also the tendency to be oxidized and become a gas, such as CO, upon heating in air. Now, this book of mine called Composite Materials gives a lot of details about composite materials and the use of fibers and various fillers in composites for structural and non-structural applications. Carbon nanofibers is our next member of the graphite family. Now, nanofiber is also called filament, and they have diameter below 1 micron, typically 0.1 micron or less. But ordinary fiber has diameter 1 micron or above, typically around 10 microns. Okay? And this is a common type of carbon nanofiber, which has a structure like a stack of ice cream cones with the tip of each cone cut off. Okay? And the cross-sectional view makes it look like a fishbone, and therefore this is called fishbone morphology. The carbon nanofiber is typically made by catalytic growth using a carbonaceous gas such as acetylene as the carbon source. And the catalyst is typically iron or nickel. And you need a reducing gas so that it wouldn't oxidize once the carbon is formed. This is a microscope picture showing the carbon nanofiber, and you can see a hollow channel in the middle, okay, a TEM microscope view. But if you use SEM instead of TEM, then you can not see the channel inside, because the SEM is just a reflective mode of operation. But you can see the nanofibers, low mag and high mag. Note that they are intertwined. Okay. Now, next is carbon nanotubes without cap. Okay. Cap means the closed ends of it. Yeah, the nanotube has the two ends closed. Okay. This is with caps. Okay. The cap actually is a hemisphere, and that belongs to the fluorine allotrope family. Okay. And so in this case, it would be a hybrid of a graphite family and fluorine family. Okay. But if I want to stick with the graphite family alone, then I want the carbon nanotube without the cap. Okay, like this. Okay, this is single wall. This is double walled. And you can see that you have hexagons as well as pentagons involved. Each wall is, you can envision it to be formed by rolling a sheet of carbon hexagons. And you can roll it in various directions. Say you roll it along this C sub H direct vector, and then you would form a tube with this vector T being the axis of the tube. But you can roll it in various directions. The C sub H can be any arbitrary direction. If it is this direction, you would end up having what's called an armchair configuration. And you can kind of see the armchair. I'll see, and this is a zigzag. This shows it more clearly. You fold it, okay, and you see the armchair here at the edge, okay. But this is zigzag. You fold it, and you see the zigzagging at the edge. And this is the armchair at the edge, and this is zigzagging at the edge. And you can roll in any direction. So this is an in-between, not armchair, not zigzag, but in-between. So these different types of rolling direction gives you different chiralities, and they can have different properties. Okay? So there are various types of carbon nanotubes. Not only how many walls, the number of walls, but also the chirality. This is a carbon nanotube TEM image showing some single wall and some double walled, but in general, it's not purely of one type. Okay? In fact, there are some multi-wall that is more than two walls, and even some amorphous carbon, that is a turbostratic carbon there. So one needs purification to get a pure form of carbon nanotube. Here is another form of carbon nanotube, and that is called a forest, which means that you have catalysts at the bottom here on the substrate, and each catalyst gives you one nanotube growing upward, just like growing hair. And so it looks like a forest. Okay? And you can take a very well-aligned carbon nanotube array and pull it like this, you can see, and you get a yarn out of it. Okay? And you can pull it not at one spot, but in multiple spots. So you have multiple yarns coming out, and then you twist the stuff, and you get a twisted yarn out of it. And this is a real image of the yarn that's drawn. And this you can see, you draw it from different points, and then you twist it together. And you don't have to twist, you can just lay them parallel, and becomes a carbon nanotube film. and you can have such a long film. Okay. Another is activated carbon. Activated carbon is porous carbon, but how do you make the pores or holes? That's made by oxidation of the carbon under heat. And this is one of the reactions that can be used for this purpose. You use oxygen, so this reaction forms CO2 gas, which comes off, and so the carbon is consumed by this reaction and becomes a gas which goes off, and so you get a hole, many holes. And you have mass loss as well as volume loss. Okay. And this is the weight loss or mass loss during heating in air. Okay, so you have the weight suddenly drops a lot. That's because of the oxidation. And different types of carbon have different tendencies to be oxidized. Some are easier than others to be oxidized. And that's why the onset of the oxidation occurs at different temperatures depending on the type of carbon material. And this is a typical configuration of the activated carbon, the holes. Okay, you have a big mouth called macropore, and then the oxidation digs in, and you have smaller pores, like tunnels, digging in, and you have the tips of these are very, very tiny, but the mouth is much bigger. So you have a gradation of various sizes of pores. But this is all accessible from the outside. Okay, this is the surface pore, but it's digs in. Okay, so as a result, you get a lot of surface area per unit volume in activated carbon, and the junk can lodge in to the pores, and thus the activated carbon is able to purify gas or liquid. Okay. And this is the most common activated carbon in the form of granules, porous granules. And this is a more exotic form, which is carbon nanofiber that's been activated. And this is another form, which is a polyurethane sponge, which has been coated with powdered activated carbon, slurry. And here's yet another form, which is activated carbon fiber cloth. That is, you activate the carbon fiber and make a cloth out of it. Okay. Now we'll consider carbon black. Carbon black is in the form of powder, but actually it is a form of aggregates. Okay. Aggregates of nanoparticles. Each particle is nano. Okay. And the surface of the nanoparticle has various functional groups on it. And the size of the aggregate is a variable. Okay. Low structure means you have very few nanoparticles per aggregate. High structure means you have a lot of particles per aggregate. And it turns out the low structure is better for conformability, because if you have a big one, it's harder to get into the valleys in the surface topography as needed for conformability. If you look at the carbon black under high resolution, one sees that there are some carbon layers, okay, but it's not very well ordered, but there are carbon layers there, a certain degree of crystallinity. Okay? And as I already mentioned, carbon black is great in the squishability. Okay? And no other carbon has that degree of squishability. And because of the squishability, it is useful as a thermal interface material. In addition, because of the squishability, it is useful as a conductive additive, say in an electrochemical electrode. Okay? For instance, you have in this electrode some big particles that are needed for the electrode operation. But you need to make this thing electrically conductive because of these big particles not being conductive. So you need to put in a conductive additive to make the overall electrode conductive. And if you use carbon black as a conductive additive, the carbon black is then squished between the stiff big particles. As a result of the squishing, the carbon black becomes smeared and elongated, and so be able to touch one another, forming a continuous conductive path. Okay? And this is an illustration that after the squishing of the carbon black, it forms an elongated path like this. And that's called percolation. And so you have continuity in the electrical conductive path, and so you have good conductivity. So carbon black is actually very effective as a conductive additive because of its squishability. Can be even better than carbon nanotube in that regard. Next, we consider intercalated graphite. It means you insert some foreign species, atoms or molecules, between the adjacent carbon layers. Here you have 2 carbon layers between the nearest intercalate layers, shown in dashed line. And here you have 3 carbon layers between the nearest intercalate layers. So in this case, we call it stage 3. This case, we call it stage 2. Okay? So there are various periodicities in the vertical direction. This is a compound. These are different compounds. And this is a case of stage 1 potassium compound. And you have potassium atoms in purple between the black carbon atoms layers. This is the side view. This is stage 1. And this is the top view, showing that within a layer, the potassium atoms are also ordered. Okay. Now, intercalation only occurs in highly graphitic carbons. Now, the structure of an intercalation compound looks like this, as proposed by Domar and Arold back in 1969. The carbon layers are the full lines, and the intercalate layers are the broken lines. And the carbon layers are a little crooked here, and as a result, you have the intercalates in limited extents, forming an island. Okay, so you have intercalate islands, and that brings us to exfoliated graphite, which makes use of these islands. So in exfoliated graphite, you have graphite flake, and you intercalate the graphite flakes, and then you heat it rapidly, and it expands, and we call that exfoliation. It's puffed up, and this is how it looks like after the puffing up. Okay, and a lot of pores, a cellular structure, and this cellular structure is due to the presence of the intercalate islands. The islands just expanding because the intercalate wants to vaporize, it's just ballooning up. And the ballooning is possible because the wall of the balloon involves a number of carbon layers, say 60 carbon layers. And the carbon layers can slide relative to one another. So the balloon wall can stretch a lot due to the sliding of the carbon layers among one another. And this is the cellular structure. And the solid line is the balloon wall, the wall of the cellular structure. And this wall can consist of, say, 60 carbon layers. And this is the exfoliated graphite that has been greatly exfoliated. And you see the carbon layers very separated. Okay? In fact, this is the mother of graphene. Okay? This is one way of making graphene. making exfoliated graphite and then shaking it to make it loose and form graphene. And this is what's called graphite nanoplatelet, which is formed by exfoliation and the shaking. But we call it graphite nanoplatelet, not graphene, because one should use the term graphene only if the number of layers in the stack is less than 10. Okay? If it's greater than 10, one should not call it graphene, but call it graphite nanoplatelet. Graphene, ideally, is a single layer. That's the original definition of graphene. However, nowadays people have loosened that definition to include up to 10 layers. Now this is an ideal picture showing how wonderful graphene is. It's both strong and deformable. Okay. This is actually idealized. It's a little deceiving because the fact is that the graphene is not available in such a big sheet, not a continuous big sheet, as implied by this drawing. It's just little pieces, okay? And between the little pieces of the graphene, that is a mechanically weak interface. So overall, it would not be very strong due to the weakness of the interface between the graphene pieces. However, graphene has some important applications, particularly as transparent conductive electrode for solar cells. And here you see the graphene, just one layer. So it's very, very thin, so thin that light can go through it, so it's transparent. Now for solar cell, you have to have light to be able to go through it, right? But you need an electrical contact so that you can get electricity out of this solar cell, okay? And that's why we need transparent conductive electrode. That's a very challenging combination, both conductivity and transparency. Metals are not transparent, okay? Graphite is not transparent either, it's black, but if it is very, very thin, it's transparent, okay? This is the graphene transparent conductive electrode. Here is graphene with holes. And there are a lot of functional groups not shown here due to the reaction involved in making the holes, and so there can be chemical sensor application. And this is crumpled graphene, just like tissue paper. You crumple it. And that can be attractive for stretchable electronics. Flexible graphite is next, and that is formed by having a pile of exfoliated graphite and compacting it to make a sheet. Because of the resiliency, it is good for EMI gasketing. Okay? And you can cut it using scissors. Applications involve not just EMI gasketing, but also regular gaskets for harsh environments, for asbestos replacement, because graphite is relatively inert chemically. Also, because of the conductivity and the flexibility, one can use it for flexible heating elements, such as for aircraft de-icing. So this completes our discussion of all these members of the graphite family. I'd like to end by saying a few words to inspire you a bit more. In research, it's better off to be a leader rather than just a follower. And to be a leader, one needs to be creative. And it's not just an incremental advance that one should focus on, but transformative kind of advance. And to attain that, one needs to have sustained work, not just 1 or 2 years of work. It could be a few decades of work. Okay? Here is what you are passionate about. Here is what the world needs. And in this overlap region is your calling. Yeah, that's your lifelong calling. And that's your homework for your life. Okay? But to succeed, one needs not only knowledge, hard working, sincerity, and humility. One needs all of these, okay, to reach success. But ego, jealousy, cheating, laziness, that would get you down. Okay. So in general, there's IQ, intelligent quotient, which is great. Okay. EQ, emotional quotient, which is the ability to keep on going amidst difficulties. But also one needs SQ, spiritual quotient, which is the knowledge of why you are doing this. What's the meaning of your life? What are you living for? Okay? And we need all three Qs to be successful. So I wish you lots of success in your life.